Good evening, everyone. My name is Dima Schlichtenko. I'm the director of IPAM. It's a great pleasure to welcome all of you to this Green Family Lecture series by Barish. I want to say a few words about IPAM and about Green Family Lectures. IPAM is the Institute for Pure and Applied Mathematics. It's a national institute funded by the National Science Foundation, and it's located on the UCLA campus. And it has a very easy-to-say slogan: math changes everything. What it intends to do is to change everything through math by bringing together mathematics and other disciplines. So what we do is we run programs, long programs, which are 3 months long, as well as short programs, such as one this week on gravitational waves. And these programs seek to attract people from all over the world doing things which are somehow related to mathematics. So the Institute is soon to celebrate its 20th anniversary. It's been a great success, and in no small thanks to Mark Green, who is its founding director. So Mark Green, who is here with us, with his wife Catherine, had a great idea to donate some money to IPAM and establish an endowed fund that would run the Green Family Lectures. So these lectures originally brought one person a year to IPAM, an eminent person, to give 2 public lectures and 1 technical lecture. And then more recently, this was expanded to 2 lecture series a year. And so this is the second one of this academic year. And we're very grateful to Mark and his family for endowing these lecture series. Let's give Mark a big round for applause. There are lots of interesting events happening at IPAM, and if you're interested in being on our mailing list or just getting announcements of upcoming public and more focused scientific events, there's no better way than to join our Frontiers Society, which is a small charity that helps IPAM with many little things. It costs very little money to join, and if you're interested, please stop by one of our staff, ask one of our staff members who will tell you more about that. Following this lecture, there will be a reception at IPAM, so if you don't know where IPAM is, you can ask your favorite personal assistant, or you can just follow the crowd. It's mid-campus, in between the math and the physics department. All right. So once again, many thanks for joining us. And so let me introduce, I'm sorry, I can't see anything behind this podium. So who's introduced? Where's the, oh, there you are, okay. Please come up so that we, sorry, I'm too short to see anything behind. All right, so it's a great pleasure to introduce Marco Cavaglia, who will introduce the speaker. Thanks very much.
Thank you. All right. Can you hear me well? Can you see me? All right. I'll try to do this way. I'm very honored to introduce today's speaker, Professor Barish, one of my colleagues in the LIGO Scientific Collaboration and a friend. And Barry's career in physics spans several decades, and I'm not going to list all the prizes and all his accomplishments. Otherwise, I'll take the full hour of his talk. But let me tell you a few things. So Barry started his career as many people in the LIGO Scientific Collaboration as a particle physicist. And over all these years, he contributed both to particle physics and to gravitational-wave physics. Today's lecture is about gravitational waves, so let me tell you a little bit about Barry's contribution to the field. As you know, in 2017, Barry was honored with the Nobel Prize in Physics, together with Ray Weiss and Keith Thorne, for his contributions to the LIGO experiment. And so one of the major accomplishments of Barry concerning gravitational waves was really get the LIGO Scientific Collaboration started. So sometimes in physics, you need vision. And Barry had this vision of a field that would expand dramatically with LIGO and the discoveries. And he had this vision to create the LIGO Scientific Collaboration, to get funding for LIGO, and to create this entity that nowadays does the science of LIGO, does research for the future detectors, and really puts together over 1,000 people all across the world in 18 countries and 3-4 continents to do this science. So this was one of the major contributions along the way of Barry. And I have to say that this happened, the LIGO Scientific Collaboration and the beginning of LIGO happened about 20 years ago. But still today, when in the collaboration we need to, fix a few things and decide how to proceed, we still, call Barry and said, what would you do, right? And how would you fix this? So without further ado, I'll ask Barry to come here to the podium, give his great lecture from Einstein to gravitational waves. It's a pleasure. Thank you very much.
Thank you for the introduction. So as you heard, I'm going to give 2 public lectures, one today and one Wednesday, and I've made them pretty separate from each other. So the other one doesn't, if you don't understand anything today, it doesn't mean you won't understand anything then. And then I'll give a more technical lecture at the conference. Let me start and proceed kind of historically today. Since we're talking about gravitational waves, we'll start from gravity. And we all learned about gravity when we were school kids because we all experienced gravity at the youngest possible age. So in school, we learned that the apple falls out of the tree because the Earth pulls on it, that the moon goes around the Earth because gravity pulls, and so forth. And at some stage, when you got a little bit older in school, you saw a formula, which I show here, which is the famous formula of Newton's, which he wrote in a book called the Principia in 1687. And in that treatise, which was his major work, he did the calculus to show that you could take, for example, the masses and take the center of that, center of gravity, center of mass of each of them and measure this, use this R. And he wrote down this formula that the attractive force between 2 masses is the product of those 2 masses divided by the square of how far apart they are, and some strength, which is this constant g, which he didn't determine and didn't know how to determine. And in fact, it took 100 years before that was determined. So Newton then actually in the Principia called his theory of gravity universal gravity because it was to apply to everything, whether it was 2 masses like these pulling each other, whether it was something astronomical, whether it's the tides, all these things use the same formula. And this is arguably probably the most successful theory of all time in physics, with no flaws as it came out and to basically describe nature. So that time proceeded with no deviations from Newton's theory presented in 1687. As I mentioned, it took 100 years to figure out how to determine this strength of the gravitational force. And that was done by Henry Cavendish, 100 years after Newton's Principia and writing down the formulas for his universal gravity. Cavendish developed something called a torsion balance, and it's shown here. And that is a rod like this with rods this way, and he would twist it a little bit, and it tries to restore itself. And he measured how much it restored itself very carefully, and then instead brought up 2 lead masses to the side and watched it deviate, and could determine then how much this attractive force was. It was the first time it was ever done that way, or done at all. It took 100 years, as I say, and then he determined that G, it has this value, 6.75 10 to the minus 11 in the units that we use. Interestingly, after 100 years, he did this, and the best number today by the Bureau of Standards is almost identically the same number. So it was a pretty terrific measurement, and that determined then capital G, or the strength of the gravitational force. So that's all good. And universal gravity was used for everything: the orbits of the planets, the escape velocity from the Earth, the tides, anything that involves gravity itself. Then this guy comes along, Urbain Le Verrier, and he was a mathematician and was labeled the father of celestial mechanics, actually, for what I'll just show you. And this is in the 1800s, so 150 years later. And he's the first one that worried about deviations from Newton's theory of gravity and Kepler's theory of planet motions. And so what he did was notice that Uranus had some deviation from using the formulas of Kepler and Newton. And he was kind of a dramatic guy. He worked the problem backwards. He thought that Newton was probably right, and the reason there were deviations was that there was some missing object that wasn't being accounted for in all the pulls on the planet Uranus. And so calculating it all backwards, he determined there was a missing planet. He was kind of dramatic, so he lived in Paris. He sent a letter to an astronomer in Berlin. He gave it 5 days to get there. And then he told the astronomer where to look up in the sky. And within a degree, he found the planet Neptune. And that was the beginning of Neptune. And this Urbain Le Verrier then became the father of celestial mechanics. And so that's Neptune. Since he was successful at that, he looked more carefully. And this is about 10 years later. And in 1850, he found another planetary orbit problem. And that's the planet Mercury around the sun. Mercury is our planet closest to the sun, and it has a very elliptical orbit around the sun. And each time it goes around, because of all the gravitational pulls, it comes back to a different spot. And you can calculate all the gravitational pulls. And if you do that, you find that the actual amount that the orbit moves each time around is slightly different, about 10% different than what you would calculate using Newton's theory. Since Le Verrier was so successful in predicting the planet Neptune, he tried the same thing for the planet Mercury. And he learned that if you put some significant mass between Mercury and the sun, you could make the orbit okay. He gave it a name, Vulcan in this case. And then there were a lot of experiments done, and people claim they found Vulcan in the 1870s, 60s, and 70s, but nothing stood up. So by the time, and the reason I'm telling this story, by the time Einstein came along, the only deviation that existed experimentally from Newton's laws of gravity, which were 230 years old, was this small deviation of Mercury from the orbit that you would calculate using Newton's equations. And later, this is after Einstein, NASA did a very, very careful scan looking for matter, either a single planet or just matter between Mercury and the sun, and found that there was nothing bigger than about 10 kilometers in size. So that was a very precise experiment, and there's probably nothing there. But it was the planet Vulcan was reinvented for Star Trek. Nevertheless, this is the stage when Einstein came along and gave us a new theory of gravity. So there was almost no visible reason experimentally why he should do this. Most of us that are physicists grew to idolize Einstein because of what he did in 1905, where he solved several of the main questions in physics within a matter of months, publishing a revolutionary publication each month for 3 or 4 months. Then he spent 10 years working on the theory of general relativity, which is adding acceleration to the theory of special relativity that he produced in 1905. Some historians use the deviation of Mercury as a motivation. It's hard for me to believe that he would spend 10 years because of that problem. But there were conceptual problems with Newton's theory that were apparent. One of them was even apparent to Newton. So he realized his theory wasn't complete. And when we have a new theory, it doesn't really mean that the other one's wrong necessarily. It means that we have a better way of looking at something in nature. So there were 2 problems with Newton's theory. The first one is that in Newton's theory, when the apple falls, you see it immediately. There is what we call instantaneous action at a distance. As when it falls, you see it right away. But that's unrealistic, and Newton knew that. If the sun were to burn out right now, it would take 7 seconds for us to know it when the light stopped coming. And similarly, it has to take some finite time, we believe, for a gravitational signal to come. So the first problem in Newton's theory is it's incomplete. It didn't account for the fact that there has to be finite speed of information travel. The second one is more conceptual, at least at the beginning, and it's one that maybe some of you asked your teacher when you were young. I didn't. And that is, you were taught when you were young that if you jumped up, the earth pulled you down. And then I gave you the formula once you learned that a little bit later. But did you ever think of asking your teacher why the earth pulled you down? Because Newton didn't explain why it pulled you down. So that's the second conceptual problem. And in fact, during the years before Einstein came, the usual explanations that people tried to make involved electromagnetic interactions because people didn't know anything else. But they were, of course, not the right one. So Einstein conceptually fixes both of these 2 problems when he has his own theory of gravity, which, as I say, was adding acceleration to a theory he presented in 1905. And by 1915, he presented his theory of gravity. Being a public lecture, I'm not going to explain this formula, which is the equivalent formula that Einstein used compared to what I wrote down for Newton, just to show that it's quantitative, not for today's lecture. Conceptually, what Einstein did is make one theory that unified space and time together into a 4-dimensional theory. This is very difficult, and it's very complicated. It's usually only people try to learn it when they're senior graduate students. In doing calculations, if you don't set it up right, you get a lot of infinities. And so it's a very difficult concept. But space and time are unified together. I'll talk about it kind of conceptually. The fact that space and time then make one word, which Einstein said, is still not understood by most people, including Bill Gates, since he puts a little wavy line under it when I write it in Microsoft Word. So, what happens conceptually in order to make the attraction in Einstein's theory? As I say, space and time are combined, And I'll just show you a conceptual picture. I can't draw a four-dimensional picture. So I'll draw a picture here of, you can think of this as a coordinate system or a trampoline if you want, but the coordinate system, which was flat before the objects appeared, the sun is here and it distorts the space around it. And the Earth is here and it makes a little distortion in the space around it. And if I take any point, it's distorted not just in spatial dimensions, but also time. And if you come out here, there's no distortion. So the way that this object is held to here is that it's falling downhill. But if it's going around, it has a centripetal force that balances it, and it goes around. Einstein realized that now that he distorted space and time, that it didn't matter whether the object that comes near it is massive or massless. So that if I have light and it comes near this distorted space-time, it'll get bent. So in 1915, when Einstein presented the theory of general relativity, he predicted that how much light would be bent if it came near the sun, and proposed that an experiment be done when the sun is in full eclipse, like here, and some stars move behind the sun, that you can see by following the stars, the bending as it goes, as the light comes past the sun. And first there was a failed expedition that went east from where he was into the place where there was a revolution going on. That was the Soviet Revolution. That mission failed because of that. The scientists that went were arrested because their equipment seemed to be something maybe for purposes other than science. And instead, it was finally done in 1919. He proposed it in 1915 in a full eclipse of the sun in the southern hemisphere by Arthur Eddington. And the amount of bending was just as predicted by Einstein. So that actually is what made Einstein a household name. The 1905 series of papers, which most of us as physicists celebrated in 2005 as a centennial, isn't what did. The bending of light, however, was all over the world and made him a household name. So those are the two obvious results of Einstein's complicated theory. First, it fixed the orbit of Mercury. And second, it predicted quantitatively the value that light would bend if it went around a massive object, in this case, the light of stars going behind the sun. The next year, I'll come to that. Before I go on to the third prediction, I want to point out one thing, that is that general relativity, which is very complicated, as I pointed out, is used in everyday life. And you often think that theories that are very complicated don't have any application. In this case, GPS, which we use in our iPhone, in our cars, in walking and hiking, are only work using general relativity, a little fact that most people don't recognize. The GPS system is something like 24 satellites that are circling the Earth at any given time. You see up to 6, and they're traveling fast. They're going 14,000 kilometers an hour as they're going around. And because they're going 14,000 kilometers an hour, then the first correction that one has to make is one that we all learned from Einstein's special relativity. The saying is that moving clocks tick more slowly. That is, if I'm on a system where I'm moving very fast, the clocks will tick more slowly. This is a well-known outcome of the theory of special relativity of Einstein's. And that correction is 7 microseconds per day for the satellites in our GPS system. There's a second correction, which comes from general relativity. This correction is because when you go up to where the satellites are, the gravitational field is only 1/4 what it is on the Earth. And so you have to make a correction for the fact that it's got less gravity. Having less gravity, the clocks go faster. And in fact, the correction's much larger than the correction for special relativity. It's 45 microseconds per day. After a lot of effort, the military became convinced when they put up the first GPS system that the correction had to be made, and it's made inside the satellites themselves. If that correction wasn't made, then you would have to ask how much 38 microseconds per day affects your movement. I won't do the numbers for you, but if you go down, I think I did it maybe, or if you ask, that's just how accurate it has to be. If a road is 10 meters wide, you can ask how long you would stay on the road without making the correction, and it's about 2 minutes. So the GPS system relies on this, and I just say it so you know this isn't totally abstract, what we're talking about. Okay, Einstein made a third prediction, and that's the subject that I'm going to talk about for the rest of the lecture, and this was in 1916. He wrote a little paper, which is shown here, in 1916, and that paper doesn't develop theoretically the gravitational waves from first principles in general relativity. Rather, what he did was notice that if he set up general relativity in a particular way, the equations of general relativity looked similar, or with different letters, of course, similar to the equations of electricity and magnetism. And since electricity and magnetism has waves, radio waves, light waves, microwaves, and so forth, he made the leap, which Einstein was good at, that there must also be waves associated with general relativity. And he made that prediction in this little paper in 1916 with almost no formulas. It's just this argument. However, the paper was kind of poorly written. It had a series of errors, one of them actually a factor of 2, which would have been pretty bad for us when we were trying to measure gravitational waves, for example. He recognized those later, and he wrote a second paper in 1918. And that corrected the factor of 2 error. Being Einstein, he never referred to the fact that he made the factor of 2 error. He just fixed it. And it contains, more importantly for the experimental work, it contains an explanation of what kind of source would create gravitational waves. And we know that in electricity and magnetism, the way we make electromagnetic waves, the way it was done to first see electromagnetic waves, is to take 2 charges and oscillate them, a so-called dipole moment, and that creates electromagnetic waves. For gravitational waves, as he shows in this second paper, it's a quadrupole formula. So not 2 charges, but a quadrupole formula. And that basically tells you the kind of system you need to make gravitational waves, and that we use to have targets of what kind of objects will give us gravitational waves. So Einstein then left the subject. Very few people picked it up. Well, general relativity itself was competing with quantum physics in those days, so most theorists worked in quantum physics, not general relativity. A few did. Einstein left this subject. He returned to it only almost 20 years later, after he had emigrated from Berlin to Princeton University. And at that time, he was working with a well-known younger physicist named Nathan Rosen. And they wrote together some monumental papers. They also revisited in 1936 the question of gravitational waves. And the reason, clearly, is he had never derived out of general relativity gravitational waves. He had only made this analogy to the formulas that looking like the form of waves and electromagnetic waves. So they had the purpose of trying to derive it out of general relativity itself, and ran into trouble. So when they tried to derive it, they ran into trouble, and they had infinities, or what we call singularities, in the calculations. And Einstein and Rosen then wrote a little paper. That paper was entitled, "Do Gravitational Waves Exist?" A rather funny title, since he had predicted them 20 years before. So you can imagine that the paper itself basically explained the difficulties they were having and the infinities that they were finding and trying to develop the existence or not of gravitational waves. That paper went to Physical Review, and there was a young editor at that time, John Tate, and this is just the time when in publishing literature, publishing scientific papers, they were beginning to use peer review. So just at the time they're using peer review in the early 1930s, I doubt but don't know what was happening in Germany for Einstein's earlier papers, but in Physical Review, just in the early 1930s, they were introducing peer review. And in fact, the editor had the latitude of deciding whether to accept a paper, reject a paper, or send it for peer review. By the way, anonymous peer review. So it goes to somebody, but nobody knows who it is in the peer review. This is the page from the logbook of Physical Review, which now can be looked at. And we looked at it a while back. And this is just an example of 3 papers that were submitted. One of them was accepted, one of them was rejected out of hand, one of them was accepted, and the third one, Einstein and Rosen's paper, the one I just referred to, was sent to a referee. That referee was named Howard Percy Robertson. He was a general relativist also, worked in general relativity. He was also at Princeton University. But at that time, he was on sabbatical at my institution, Caltech. So he was at Caltech. He gets this paper to review of Einstein and Rosen's. And he recognized the problems they were having setting up the problem in this coordinate system. And he basically, instead of having this single coordinate system that had these what we call coordinate singularities, he set the problem up in what are called cylindrical coordinates, and they went away. So he sent back a report to the referee, a referee's report to John Tate, and John Tate, you have to imagine, is in a pretty awkward position with Einstein. And he sent a letter. I didn't copy the letter here, but it's incredibly mild. It's not the kind of letter I would get or you would get. It basically says, I'd be glad to have your comments about the referee's comments and criticisms. Einstein didn't take that very well. And he wrote this letter back, and this one I included. So he answers the editor, John Tate, by saying, "We, Mr. Rosen and I, had sent you our manuscript for publication and not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere." And that's what he did. He sent the paper then to a journal at the Franklin Institute in Philadelphia. Franklin Institute is a big institute that still exists. At that time, they had a journal, which they no longer have. But at that time, even we complain now when we submit an article for publication that it takes too long for the referees and too long to publish. But in previous times, there was all the problems of copy editors and fixing the type, and there was a long process in actually ending up getting a publication. Fortunately, in this case, for Einstein. So after several months, it turns out that Rosen had gone back to Europe. Einstein had a new assistant, Infeld, who was quite a well-known astrophysicist later. And he was working with Infeld. At the same time, this Howard Percy Robertson returned from his sabbatical at Caltech to Princeton. And when he returned to Princeton, he was an anonymous referee, of course, but he got into a conversation with Infeld where it was academic because he didn't say he was the referee, where he pointed out how you could set up the problem, and the singularities that were found were mathematical and not physical. We don't know the rest of the story because Infeld presumably talked to Einstein. The myth is that Einstein said he saw the errors the previous night or week or something. We don't know. But anyway, the paper was changed and was published, but it changed its name. Notice it doesn't say what it did before. Now it says On Gravitational Waves. And it starts with a sentence, if you can't read it, the rigorous solution for cylindrical gravitational waves is given, which is kind of what the referee did. So that's Einstein's last time in his life that he referred or said anything about gravitational waves. That's 1936 with this little anecdotal story. It still wasn't universally accepted by people, even in the field of general relativity, that there were gravitational waves. Clearly, this paper didn't solve the problem, and nothing else much was written. If you try to trace when it became legitimately agreed to by the theorists in the field, I think this is the time. That is a conference that happened about 20 years later, in 1957 in Chapel Hill, North Carolina, that pulled together about 44, I guess it says here, of the leading general relativists in the world. And that meeting was called in order to work on the so-called gravitational wave problem, which wasn't solved. A theorist named Pirani, who lived in Britain, gave the first talk at that meeting, and in that talk he gave a very elegant derivation of gravitational waves from general relativity in a very theoretical way. And that, for most of the theorists, I think went a long way in making them believe that gravitational waves did exist. A second person who was at that meeting was my old colleague, Richard Feynman. And at that meeting, he did something complementary to this and something that was typical of Feynman. He said, if there are gravitational waves, then they must be able to exchange energies. Otherwise, they just go through space. And he went the next step and made an argument how that would be possible. And that's what Feynman called the sticky bead argument. The sticky bead argument was that if I have a rod like this and put a couple rings around it, and then gravitational wave comes in through, gravitational wave distorts the space, you remember. So it'll distort the space and create a little bit of friction between the rod and these rings, and they'll move however they move as the gravitational wave comes through. That little simple picture was the physical argument that was combined with Pirani's theoretical argument, and people came out of that meeting believing there were gravitational waves. Since I'm an experimentalist, you can account for the fact that I've now argued away about 40 years, blaming it on theorists not knowing whether there was any gravitational waves, instead of saying it took 100 years for us as experimentalists to find gravitational waves. But by about 1960, we basically now had a problem for experimentalists. And that was attacked almost immediately. But first, let me tell you what they do, and then I'll show you how the history from that point on. First, the gravitational waves themselves then are like other waves, are ripples in space, but the difference, at least in the classical picture of Einstein's, is that they are ripples in space, time itself, and don't have associated with them, for example, the equivalent of electricity and magnetism having photons. So they're much more like throwing a stone in a pond, and the little waves that ripple out are just in the water themselves. The stone went to the bottom. So the waves are waves, but they don't have anything associated with them in the classical theory of general relativity. If I go through how space is formed and what we understand about it, the amplitude of the wave, which is the amplitude just like in electromagnetic waves, is incredibly small. The number that I'll grab is the number that corresponds to the detections we made, a number of 10 to the minus 21. That's a tremendously small number, as I'll show you in a few minutes. But the fact is that if I think of what makes up space, if you just think of maybe the formulas of materials, space is incredibly stiff. Its constants are incredibly stiff, so it just doesn't bend very much. That's why the numbers are so small. The phenomenon can be there, but the numbers themselves are very small. So how small, and what is the effect? The effect is to change a distance by some fractionally by this 10 to the minus 21. This is a term that's in the general relativity called the strain. So if I had a ring like this of free masses, just imagine they're there, but they're free to move. Then if a gravitational wave came through the board, what would it do? It would make this elliptical and change the length by 10 to the minus 21 meters if this was 1 meter across. So that's the amount that it would change, as I say, because space-time is so stiff. That's a tremendously small number, and that's the challenge that we had starting, say, in 1960. The number itself is the number that I detected. I'll reflect on that a little bit. But first, let's see what that means. First conclusion is this is 1 meter. So if I'm going to be an experimentalist and try to determine gravitational waves, the first thing is to try to make this much bigger. So the detectors that I'm just going to talk about just a little bit today, and I'll talk about it on Wednesday, are kilometers in size instead of meters in size. So we gain a factor of 10 to the 3 and make the problem a little bit easier. Instead of 10 to the minus 21 meters in these big detectors, we have to measure 10 to the minus 18 meters. That's still an incredibly small number. So let me reflect how small that is. We all know what a meter is, so that's okay. A human hair, I don't have many, but for most of it, you can see a human hair with your own eyes, and it's 100 microns, and that's 1/10,000th the size of a meter. Okay, we'll go smaller. The wavelength of the light in this laser beam that I'm using here is 100 times smaller than the human hair. So it's about 1 micron. So we can all kind of reflect on that. The atomic diameter, if we get to atoms, how big are they? They're actually 10,000 times smaller than the wavelength of this light. And they're 10 to the minus 10 meters. So that's the atomic size. Now if I go to the nuclear size, and that's the size of particles that we use that we're made up of or that we study on big particle accelerators, they're 100,000 times smaller than the size of an atom. And so they're 10 to the minus 15 meters. And we have to actually measure an effect that's 1,000 times smaller than that. And so that's why this is an incredibly difficult problem, and you have to develop special techniques to do that. I'm not going to concentrate on the techniques themselves today, but I will later in the week. Okay, so then we have these distortions in space-time, and we now want to detect them. In order to make a quadrupole moment, one way is to have two objects that are going around each other. And if I have two objects that are going around each other, they'll make waves, and gravitational waves that'll go out, and they'll go at the speed of light, which is, in Einstein's theory, there's only one speed, and that's the speed of light. So they propagate away at the speed of light. So that's the phenomenon that we're going to try to see. And now I'll be a true experimentalist. I learned when I learned to be an experimentalist that one absolute point, if you want to get experiments right, is to control all the variables. To control all the variables here, you'd like to reflect on how did we find out that there were electromagnetic waves. And that was a nice experiment. Hertz in the 1880s took two charges, remember I talked about them, oscillated them in one room, and that made electromagnetic waves. He went in the next room, made a detector that saw the electromagnetic waves, and then he moved the detector forward and backward and saw it was wave-like. And that was the discovery that there were electromagnetic waves in the 1880s. So we should try to model what we do as experimentalists to see gravitational waves around what Hertz did for electromagnetic waves. So here's an attempt to do that. If I go into my lab, it's not a very fancy lab, and I make a barbell, and the barbell I'm exaggerating the numbers as much as I possibly can to make a point. So imagine I put 1,000 kilogram weights on each side. This is, say, a meter. And then I spin it. And I spin it at 1,000 hertz. I better get out of the lab. And then go in the next room and look for gravitational waves. I go 300 meters away. 300 meters isn't far enough to do what Hertz did, which is to see the gravitational waves, then move forward and backward. I'm trying to exaggerate to make as big a signal as I can. If I do this and calculate it, what I get for that same little h is 10 to the minus 35. So a man-made source in a lab, exaggerating as much as I can possibly get, would be a size that's 10 to the minus 35 to be compared with the h of 10 to the minus 21 that I talked about in the signals that we saw, because we used not our own source, but what turned out to be some black holes, which I'll come to. So the effect itself is incredibly small. We need something that's going to make a very big signal in order to see it. And what we observed, and I'm going to show you how this comes about, is the same thing as a barbell, two masses going around each other, emitting gravitational radiation. But those two masses, as I'll show you how we know what they are two black holes, each 30 solar masses in size, separated by about 100 kilometers, and spinning around each other at about 100 hertz. I'll come back to all that. If I do all that, then I get a number that you can forget the formula here, but a number that's something like 10 to the minus 21. So the difference between us doing what classically an experimentalist should do is a factor of 10 to the 14th or something. So we have to rely on nature. And although that's a danger for experimental physicists, we're lucky because the source that we found has intrinsic interests. So we learn a lot about black holes, which is kind of nice. Okay. If you recall, in 1957, Feynman made an argument called the sticky bead argument. This argument was picked up by Joseph Weber, who was a very clever experimentalist and the only experimentalist who was at the Chapel Hill meetings. So he made a big bar of aluminum. So this is very pure aluminum. This is one of his first ones. A cylindrical bar, a couple meters long, and he put sensors around the waist of it. And if a gravitational wave goes through, it distorts the bar. And that creates a little bit of pressure on these sensors. They pick up the signal, and he would see gravitational waves. So that was the idea, very much like the sticky bead argument of Feynman's. The first one he made in 1960, just 3 years after, using these bars. And the bars are not just bars. They're very pure aluminum. And you can imagine that if you strike that bar with a hammer, there's some frequency at which it rings. And that's the frequency where it's the most sensitive. So this is sensitive at roughly 1,000 hertz. And that technique he pursued for years, but the first one then was picked up using these PZT detectors. In 1969, 9 years later, so he started in 1960, in 1969, he claimed that he saw gravitational waves. That was published actually in Physical Review Letters, so the referees didn't have any reason to violate it. This is the signal. This is the picture from the figure in Physical Review of this claimed discovery, and this little peak was seen in a detector that was near Chicago in what's called Argonne Lab, and one at his university in Maryland, 1,000 miles apart. And he attributed this to being a coincidence seen in these two different laboratories and being gravitational waves. Unfortunately, this result didn't stand up. Others did the experiment better and saw that he wasn't correct. He was a tremendous visionary and did a lot to actually start this field, but not a very good scientist because he wasn't very self-critical. He published 2 more times in his lifetime that he thought he saw gravitational waves, and again, both times they were disproven. But his legacy is built into our work, and I want to note that. He basically was the first to do the kind of sensitivity calculations we need to do, and we do in our detector when those of you listen to me talk about it, in order to understand the intrinsic noises that limit your ability to measure the signal. Second, he did this coincidence, one in Argonne, one in Maryland. Clearly we copied that too. We have one, which you'll see in Louisiana, and one in the state of Washington, where we asked them to be coincident within the speed of light. And lastly, he had a way to determine backgrounds, a technique called time slices for background estimates, and it is also the same technique that we use. So we inherited a lot from him, even though our technique is completely a different technique in how to approach the problem. And unfortunately, he got lost in trying too involved in trying to make a discovery which he wasn't able to make because he wasn't sensitive enough. So using that technique, I won't show more of that. The technique evolved through the 70s, 80s, and even into the 1990s, making it more and more sensitive, especially by cooling it, making it much colder, but never as anywhere near the sensitivity that I'm going to show you we have. And no detections were found, at least nothing that stood up. So as we enter the 1990s, there was a new attempt to see gravitational waves, which resulted in the first real evidence that gravitational waves exist. Not a detection of gravitational waves themselves, which will be deferred to what I show you we did, but indirect evidence that gravitational waves were observed. These 2 gentlemen were called Hulse and Taylor, were studying a pulsar system. That's a system of a spinning neutron star, and they noticed, called PSR 1913 plus 16, and they were studying it with a radio telescope. And I think I have it on the next slide. Well, first, they're neutron stars that they're detecting. What is a neutron star? Let me remind you. It's a star, it's a product of a collapse of a star that has a mass of about 1.5 times the mass of our sun, has a crust maybe 1 mile thick. It's 12 miles across, and it's very dense nuclear matter. We call it a neutron star. So they looked at a neutron star because a spinning neutron star can have currents that make radio signals. And if they make radio signals, you see the signals every time the pulse points towards you, shown here. So as it's going around, it's radiating radio signal, and it's like a lighthouse. When it comes around and happens to point to you, you see it, and it might be 10 times a second, 100 times a second, and that's a radio pulsar. So they were studying a radio pulsar called PSR 1913 plus 16 in detail. And their objective was to measure this pulsar system in great detail, better than anyone had done before. And so they did a long-term measurement of it. It was going around, they're studying this pulsar, it was going around about 17 times a second. And they noticed after a while that 17 times a second was modulated about every 8 hours. And after a few years, they determined that this had to be a system that had 2 neutron stars instead of 1. This one, when it was going around this one, modulated the signal from this just a little bit every 8 hours as it passed by the orbit. So if that's true, then this turns out to be a laboratory that's emitting gravitational waves, because this is looks like what we'll see later. This is going around. Every time it goes around and bends, it's accelerating. If it's accelerating, it radiates by Einstein's theory and comes around and slowly spirals in. What they're viewing here is 1 million years earlier than a system that we study when they finally merge together. It takes 1 million years or so for this to merge together. So this is what they looked at, and they determined that the parameters, very definitely, they knew this was 1 million miles apart, the separation between them, that the masses of the 2 objects were 1.4 and 1.36 times the mass of our sun, and that this orbit was elliptical with a constant that determines how elliptical that orbit is. So they determined that very, very accurately. And from that, they can make predictions using general relativity of how much this will radiate if there's gravitational radiation, which is gravitational waves coming out. If you do the calculation, the spiral changes by about 3 millimeters each orbit, and that changes how long it takes for this to go around. It's slowly coming around faster and faster. They measured this over about 20 years, and that's shown here. So what they show here is the time it took for them to go around as a function of year over 20 years, and it gets to be shorter and shorter. This is 5 seconds, 10 seconds, 15 seconds, 20 seconds. So it's about shorter by about 1 second out of 8 hours every year. And the little dots that you see are their data, and the line through it is the calculation that I show here using these parameters, not a fit to the data. So we usually do a fit to the data. This isn't. It's actually a calculation using general relativity and the radiation, and it falls exactly on the data they have. From that, they won the Nobel Prize in 1990 something. I don't know exactly. And that was an indirect proof of gravitational waves. During the same period, we were converting to a new technique to try to see gravitational waves directly, which I'll talk about in a different lecture in some detail. And this was aimed at directly seeing gravitational waves from a source like they're showing, but a source seen in its last breaths, where they're really coming together, because that's when the gravitational wave signal will be the strongest. This is a picture of our detectors. As I mentioned, the only thing to notice right now is that they're kilometers in length. So these are buildings. You can see a few cars around and so forth, so you can see these are big. Also, you might notice the topography is very different. One is in high desert in the state of Washington, and the other is in the basically swampy forests in Louisiana. And we built this starting in 1994. As I say, I'm not going to go through the technical, much about the technical parts today, a little bit. But the project that built this is about 178 physicists, engineers, grad students, and so forth total in 2 institutions, Caltech and MIT. So this is the group that was funded by the National Science Foundation and built and is responsible today still for the instruments themselves. Okay, this is how an interferometer works. So what I have is a light source, and it goes down the 2 arms. When the light comes back, it should come back at the same time if the 2 arms are equal. As we'll see, it just hits a mirror, comes back. When it comes back to here, if they come back exactly the same, they'll cancel each other. They'll be just opposite. and this will be light-free, won't have any light. If one of the arms changes with respect to the other arm, then they can add to each other, and you start seeing signals in the detector that's here. That's a simplified view of what an interferometer is. We have to make this interferometer incredibly accurate, and I'll talk about that in another lecture, what tricks we use to do that. So that's the scheme of interferometry, which is what we use. Now, to continue the story of the detection, the story actually began, since I started historically talking about the human part of the story, starting from Newton, I'll start historically here too. It goes back further. The detection story actually began 1.3 billion years ago. And 1.3 billion years ago, there were two objects which we've recreated here from our data. And those two objects are what we managed to detect as they merged into each other. Those objects we know from our data are what are called black holes. But let me remind you what a black hole is, at least at the level that I need to for this lecture. So you read about black holes all the time in the newspaper. The black holes I'm talking about are basically a place in space where matter is so dense that nothing can escape, not even light. And that's due to the strength of gravity itself. You remember that light bends in a gravitational field, as I showed in the earlier. So nothing gets out. That's why we call it a black hole. Now, more physically, some black holes can form when a star, like our sun, but not our sun, ends its lifetime. So what do we mean by ending its lifetime? A star burns by what's called the nuclear fusion process. It starts with the light elements, and it burns them up, slowly works up to where it's burning heavier and heavier elements. The fusion process is pushing outward, and gravity is trying to pull inward. And it happily is a bit balanced during the lifetime of the star until you get up to heavy enough elements where there's not enough fuel to balance the pull of gravity, and the star collapses on itself. We call that a supernova. And when it collapses on itself, there's a final dense product. If that product is dense enough, it can be a black hole. Our star, the sun, isn't heavy enough. We think the lightest star that can make a black hole has to be about 3 times the mass of our sun. So our sun, when it collapses, will make something like the neutron stars or something else, but not a black hole. So that's a black hole. We think the ones that we've detected come from the decay from the collapse of a star, but a much heavier star than was seen than our own star, our own sun. This is a recreation from the general relativistic calculations fitting our data of what we observed. You'll notice the star, I've slowed this down a little bit. The stars that are around it are moving, look like they're moving. That's the bending of light that we were talking about. So they're affected by the presence of the black holes themselves. The black holes merge together, and then there's a little settling. Just if you remember that physical picture, when I show you the signal, it'll remind you of that. So that's the black holes. Let's put it in perspective in the picture when we see it. Here's a map of Los Angeles. And what we see by the time it enters our field of view is put on top of here. So if I take Westwood here and go down to, say, Irvine, that's the separation of these two black holes. They each have the first ones we detected, each have about 30 times the mass of our sun. So they're heavy enough to satisfy the criterion that I said. And let's put that in perspective. 30 times the mass of our sun is 10 million times the mass of our Earth. So we have an object here this big, about the size of West LA or the size of the bay down there, which is 10 million times the mass of our sun, of our Earth concentrated in this small distance. They're separated from each other by 50 miles or so, and they're going around each other by the time they enter our apparatus, also highly relativistically at about half the speed of light. So this picture is kind of unbelievable to absorb, but that's when the last instants are before they merge together and why the signal is so big that we can detect. So they merge together. As they merge together, which is shown in this movie here, they emit, by Einstein's theory, gravitational waves. Those gravitational waves have been passing through the universe for 1.3 billion years, coming toward the Earth. As we said, they're going to distort space and time. So as they pass through the Earth and they get higher and higher frequency, they distort the Earth more and more. This is, of course, exaggerated just a little bit. And then they're gone. So that's what we see. We can't, the actual distortion of the Earth moves enough itself, we couldn't possibly come close to seeing. So instead, we have to build an instrument on the Earth that can see this stretching and squashing. That's the so-called interferometer, using the techniques that I said. So this arm might get a little longer, while this one gets a little shorter, and we determine that in this very sensitive device called an interferometer. Okay, and I showed you this. Okay, so what are the challenges? Without going through the instrument at all, what we have to do is measure this change of length to something like 10 to the minus 21. If I put in the numbers of what that means, we have to be able to tell in terms of the wavelength of the light that we use in the laser. It's not exactly this wavelength, but similar. We have to be able to what we call split a fringe, if anybody's used an interferometer, to 1 part in 10 to the 12th. That's unprecedented. People do interferometry, but not nearly at this. So part of why it took us so long is developing the most sophisticated interferometer ever developed anywhere, with as many tricks, high power lasers, fantastic mirrors, and so forth, and a big size in order to do that. The second challenge is that we have to get rid of the fact that the Earth is moving around much more than what we want to measure. We have to isolate ourselves from the Earth also to 1 part in 10 to the 12th. And that is a real challenge. And it's the final challenge, although I won't go through it today, that we beat when we were able to finally make the detections. So as isolating ourselves from the Earth was what we took many years before we could do well enough. Anyway, to continue the story, on September 14th, 2015, up from the southern hemisphere, and we know this banana-shaped region by seeing at what time and what the signal shapes were in the 2 different interferometers that we saw. I'll show you those signals in a minute. We know it came up from the southern hemisphere in this banana-shaped form, which is 1,000 square degrees, not very accurate. Today, we've made these interferometers so much better, and we've added one in Italy, that we can do this more than a factor of 10, almost a factor of 100, better than we did initially on this detection. This is the signal. So what is it that we know so quickly that this is gravitational radiation? Let me show you the picture. This is time. This is 0.2 of a second from here to here, so not very long. This is the last 0.2 of a second when these objects are coming together. This is the vertical scale. It's what I call the strain, little h. This is in units of 10 to the minus 21. You remember the number I keep using. So 1 unit here is 10 to the minus 21. That's the biggest this signal gets. So we're seeing a signal that's somewhat less than 10 to the minus 21. You can see that it's jagged. That's because there's basic noise in our system at that level. But what we see is it goes up and down, up and down, up and down, narrower, narrower, and bigger, 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 and so forth. Okay, so it turns out that 7 milliseconds later, we see almost the same picture in a detector that's 3,000 kilometers away in Hanford, Washington. Just the color's different. The wiggles are slightly different, but not very much. In fact, if I put them on top of each other, they don't look very different. Now I've drawn, and I'll turn it off and on, a little line through it. And this is what convinced us almost immediately that we'd seen gravitational waves. You can barely see the line. And the fact that you can barely see the line is because it fits the shape so well, and it's the direct calculations, no corrections, just the direct calculations from Einstein's theory of general relativity for the merger of two black holes that are the masses that I showed you. So that's the picture that we had, and that's the evidence that we had when we made the first detection. Just to show you what we're seeing then, this is the theoretical curve shown here of what you'd see by the time. Of course, it all exists back here with lower frequency, but we don't see that. We see the frequencies on the Earth that are basically the audio band, which is nothing audio, but what we have available to us to see. So once they get up to a frequency of 10 hertz or higher, we can see it. We only see 8 or 10 cycles on this merger. At the beginning, they look something like the picture that I drew. They get closer together, they come together and merge here, and in the end, they have to ring, what we call ring down. If you look at the picture down here, it shows how far apart they are, which I showed you on a map already, but this also shows how fast they're going, and by the time they're merging together, they're going at about half the speed of light. So that's the picture of what we saw. In 2017, my colleagues, Ray Weiss and Kip Thorne and myself, got the Nobel Prize for this piece of things. But my main message now is that this is not the end of the story. Since then, after that, we've seen 10 versions of 10 other events of black holes coming together. And we published this just recently. This is the waveforms we've seen. Some of them go for a long time with many waves. That's because they're lighter. And some are different masses. And all of these together start to give us the picture of how these black holes are formed, how they come together, whether they're how they're spinning relative to each other, and so forth. And that's we're studying and how well general relativity works. Those are what we're basically studying as we accumulate more data. In addition to that, we've seen a different kind of object, like I said our Earth is, and that is the merger instead of two objects that are not black holes, but are what we call neutron stars, the objects that you end up with if you don't have such a strong gravitational field that light can be emitted. And this, which I'll show in another lecture, gives signals that can be seen by astronomical objects, and they have been. So those will be the subject of another lecture. I want to end just by saying where we started, and that all of this scientific work has been done by, I like the fact that we have flags in the room, because it's been done in our case by scientific collaborators in 18 countries, more than 100 different universities or institutions, and I think 1,200 and some collaborators. The pictures are the different people who have been the leaders of this scientific collaboration. So with that, I'll end for today. Thank you.
All right, so if anybody would like to ask questions, we have some microphones here lined up. So if anybody would like to come up and ask a question, please, be shy.
You said that space-time was stiff. Can you say more about that?
Oh, that's more of an analogy than anything. We know how to take something and characterize it with things like Young's modulus. We learn in physics. We don't really think of space or characterize it as a static system like that, but it's a good analogy. There's different materials that are either very pliable or very stiff. In our case, space is really hard to warp. It just doesn't warp very much. It's just a loose analogy that I made.
In the sticky bead analogy, where you have the beads going on the rod, if a gravitational wave goes through and the beads move, does the rod stay put or does it also stretch? And if it stretches, where does the friction come from?
The rod expands, just like this man Weber was trying to see. So using the rod itself, it expands a little bit. As it expands, it puts some pressure on the beads. It expands in a wave-like form, and so the beads actually get moved a little bit, and that's friction, which makes heat. That's it. That's just a picture, but that's essentially what then this physicist Weber tried to do with instruments afterwards.
Any other questions?
What do you see the limit to the increase in sensitivity in your devices going out into the future?
Okay, the question is how much better can you make these devices in the future? We are not limited by nature itself at this point at all. We're probably a factor of 10 to 100 away from where we have to deal with some problems living on the Earth that are there. So we can improve it somewhere between 10 and 100. Not this instrument necessarily. We may have to make a new instrument. Some of the ways you can improve it, I'll just mention. You can make it bigger. Okay, that's obvious. You can put it underground. Underground, the Earth shakes less. You can cool the temperature of the system instead of at room temperature at lower temperatures. All of these would improve it, and we estimate that those kind of improvements could improve us by somewhere between 10 and 100. Now, don't be fooled. A factor of 10 is a factor of 10 because we measure what's called an amplitude, a factor of 10 further out that we look. So if we improve at a factor of 10, we improve how much volume of the universe we look at by 10 cubed, so a factor of 1,000. So the gain that we can make is quite big. That's not the whole story. We can look at different frequencies. So on the Earth, we look at the audio band, basically, because that's where the Earth is quiet. Our ears have learned that. We're not doing anything audio, but it's where the Earth doesn't make as much noise, by going in space. And there's a mission called LISA, funded by the European Space Agency. Some of us are hoping that NASA joins as well in the future. And it is scheduled for 2030 something, and it measures different frequencies. Just like you use in astronomy, instruments that are in the infrared, ultraviolet, visible, and so forth, X-ray. And in gravitational waves, again, you'd like to look at the whole frequency band. And so we know how to go to lower frequencies, and you can go to lower frequencies yet by another technique, which I won't mention.
Hi, nice talk. You started with a desire to prove that gravitational waves exist, and you've proved it, and now you're collecting more and more instances of it, but the proof is over. So what are you doing with these new instances?
Okay, thanks. So yeah, why don't we just close up shop and go home once we saw that gravitational waves exist? Look, there's two reasons. The first one I would say is very much, I'll be presumptuous, it's very much like Galileo. So in 1607, he was the first one to take lenses that were made for glasses and put them in a telescope, and he looked at Jupiter, and he saw that Jupiter has 4 moons. And that was the beginning of modern astronomy. In a sense, we've just scratched the surface of the first thing we can possibly see that is due to gravity looking at the universe. So the first goal, long-term goal that we have is to do astronomy in a new way, using gravitational signals instead of signals having to do with electromagnetic waves. And there's a whole range of possible things that we could detect, including maybe, just to pick one, someday signals from the very early universe. So we all wonder how it all began. And when we look in the best way we can now, which is with electromagnetic radiation, we can only go back to about 400,000 years after the Big Bang. That's because the photons all got absorbed. If you really want to see early, you have to have something that didn't get absorbed. Gravitational waves are the best possible source because they didn't get absorbed. We can't do that yet. Excuse me. We can't do that yet, but that's a long-term goal. The second is a physics side, and that is general relativity really right? Not whether there's gravitational waves, but is it the ultimate theory of relativistic astrophysics and what it tries to do in gravity? It can't possibly be, can it? Because we have two theories, and we have a quantum theory of nature for short distances. We have general relativity, never the twain shall meet. We have to bring these together somehow. And so to do that, we need to study general relativity very, very well and try to understand where, if we can find it, it starts deviating from Einstein's equations to give us some clues how we can possibly bring together quantum physics and classical physics. So those are some of the really big long-term goals.
And maybe one more question, and after that, don't forget that there's a reception, the poster session at IPAM, so we should all walk over there.
So you have detected a good number of collisions of black holes and one collision of two neutron stars. Are there, and you just mentioned other events that you still hope to detect. Are the events that you expected to detect with the precision you have now and have not detected, which would be indication that there's something out there that we do not understand?
Yeah, I'll take the spirit of the question. We were looking for these events. We saw them. Is there any evidence for things that we're not looking for? That's a hard question, by the way. So we have many things that we're still looking for that we haven't seen yet. We have to make more sensitive detectors to look at those. One part of this big research group that we talked about, the LIGO Scientific Collaboration, is looking at what we call unmodeled sources. So what do we mean by unmodeled? It means we don't know what they are. It's not easy to look for something we don't know what you're looking for. So what we've done is develop a technique which is not totally satisfactory, to use a mathematical technique using wavelets to try to make kind of waveforms that aren't biased by all our physical prejudices. But that's not really the ideal way of doing that. We're looking also at using machine learning as a way to look at all our data and find things that are anomalous. But it's a problem that so far we don't have any success, as I say, but we're working on it.
All right, let's thank Professor Barish again.